I'm Horton Newsome, and one of Roger's team members on the Curiosity Mars rover and also on Perseverance. And it's a really great pleasure to have him giving the talk today. And he sent along a brief bio. And Roger's, so you can see how some of the many things he's done. Of course, it was exciting when we wrote the proposal for the Curiosity, the Mars Science Lab, and we wrote some of that in Northrop Hall, and had a meeting with the French there, and that was pretty cool. Some of the our French colleagues were pretty upset that we had bagels with strawberry cream cheese. The idea of strawberry cream cheese was shocking to some of our colleagues, but Roger's done a lot of huge number of things. In fact, if you look at his bio there, he actually left out one of his most important jobs. He was the deputy science was it science lead for Genesis.
Yeah, I was a flight payload lead, and we developed one instrument. So I don't know if this will show. In fact,
it's there it is. So Roger started off helping with something very important for our Mars meteorite work, which is he worked with the group that showed that the certain meteorites actually came from Mars, from a comparison of the rare gas isotopes, and then went on and did work at Caltech, where he got involved with some of these other missions. And the Genesis project, they actually is one of the main sources of information on the composition of the sun, especially some of the isotopic ratios, which have been very important for interpretation of meteorite research. And then we got into the work on the rover, and in particular LIBS, and I was fortunate to get involved quite a while ago on a Marsicod test mission, and that eventually led to the proposal for ChemCam, and then more recently SuperCam. And as you'll hear, it's quite a story, and in fact the SuperCam is completely amazing, a follow-on. And so really look forward and really glad to have you, Roger. And so we'll let you take it away.
Well, thanks, Horton. And if you cannot hear me, please give a shout out in chat or vocally or by phone or something, so that I.
Sounds good, Roger.
Great. You know, I'm so excited to be on this mission, but I really wish I had two sort of parallel lives to live, because Curiosity is having such a great time. And so it's hard to keep up with both of them, but it's a great problem to have. And I hope that, of course, if you have not voted, please leave immediately and go vote. But otherwise, I hope this really distracts us. One of the features of Mars that's really great is that it is a nearby planet that has no politics on it. So let's enjoy this hour, and we'll have to come back to reality later, but this is good for now. So first of all, I got to make sure my slides will actually advance, which they're not doing. I hope things have not frozen completely. There we go. So first of all, I want to give a tribute to those who have put a lot of sweat and blood and tears into these instruments. And so here are the names of people here at Los Alamos who were involved in both SuperCam and Sherlock. We built part of Sherlock here and then delivered it to JPL, and it's a JPL instrument. But we did the sensor and the electronics, especially thanks to Tony Nelson, who led that. And then on SuperCam, we are leading the effort, we built part of it, and the French built part of it. And then also a shout out to the people in the chemistry division that provided the fuel for Perseverance's nuclear power. So there's several hundred people here that have really been involved with this mission. It's a big deal here. So this should show you the pictures or caricatures of the two rovers. they are effectively twins in many ways with very different instruments and different purposes that we'll talk about. So Curiosity, of course, has been on Mars now for 8 years. It has 10 instruments plus the drill. It weighs a little under 1 ton and is in Gale Crater. And then on the right-hand side, Perseverance launched in late July. It is due on February 18 to land in Jezero Crater. And it is, as of last week, it is halfway to Mars. So it's coming fast. It has 7 instruments, and it also has a sample cache and a helicopter, and we'll be unpacking all of that. And this is a little over 1 ton, and it's about 6 centimeters longer than Curiosity. It's a stretch version of it. They figured out they could get that much more into the capsule, and it's got wheels that are more durable than Perseverance. So these were redesigned to go a lot farther. And a few other things to improve on what we learned from Curiosity. So the goals of the respective missions are as follows. Curiosity is to assess Mars' biological potential, and we've done that in spades. Curiosity was the first mission to work on organic detection on Mars since Viking. And it's really showed that in a great way. We're still actually learning a lot more even as we speak on the organic materials on Mars. And that's an exciting story to unpack, not done yet at all. And then characterize the geology of the landing region, study Mars' past habitability, and characterize human hazards. We have to remember that 9 years ago, before Curiosity landed, there were people that thought that water on Mars was a very ephemeral thing. We know now that at least Gale Lake existed for over 1 million years, and potentially a lot longer. So these things are now well known, but they were not then. Perseverance, by contrast, in comparison, is going to also explore a new landing site, assess ancient habitability in this new crater lake that it will be exploring, and now seek signs of ancient life. We know there's organics there, so let's look for either extinct or extant life, most likely extinct in the sort of microbial nature, and to also gather samples that could be returned to Earth for by a future mission. This is the big thing that this mission's really doing. And then also demonstrate technology for future robotic and human exploration. So it is really doing a lot of new things. There's no question about it. Now, when we talk about the payload, which is completely different on these two instruments, I'd like to talk about the architecture. A good set of instruments will really complement each other. And so you have at the top of this funnel, and you'll see why it is a funnel in just a second, you want to put the rapid measurements that you could do very many of these measurements that will help you constrain where to make the most sensitive measurements that might take a long time. In the laboratory, we have both types of measurements, and you can take especially the rapid type of measurements out in the field. So on Curiosity, ChemCam and MassCam were the sort of the rapid remote sensing instruments. We have more than 800,000 ChemCam spectra down from 8 years. Proximity measurements represented by APXS, and then for drill sample analyses, ChemIn did those analyses on MSL to provide the X-ray diffraction, but only about 30 measurements. So that's a big difference. And so you want to constrain and make the most of those time-consuming measurements. So Perseverance is the same way. And if we put these alongside, then SuperCam and MassCam Z are providing remote sensing. Sherlock, Watson, and Pixel are providing proximity measurements. And then the sample cache is actually fulfilling the role of this very few measurements. Those would be the ones that we plan to bring back to Earth. And then, of course, there are also several other instruments. There are the environmental instruments, META, which is weather, and RIMFAX is a subsurface radar that I'll talk about in just a minute. And then there's a helicopter and the oxygen production. So we're going to unpack those. First, just this reminder that there's a real evolution towards finer scale. On Curiosity ChemCam, is the fine scale measurement for compositions. And it's the only instrument that can do that at the sub-millimeter scale. And the science definition team that convened in 2013 noted that and said, we have to have more fine scale instruments. And so Perseverance is going for those fine scale measurements, as you'll see with the ones on the arm as well now, the proximity measurements as well as SuperCam. So we'll unpack that in a few slides after this. But I like this caricature of the rover because it really starts to spell out what these instruments are. And so I like to categorize them into these groups that I just showed you. So here we have the remote sensing, we have proximity on the arm, and then we have the environmental instruments, so RIMFAX on the back of underside of the rover, and then META, which is on the deck and on the mast of the rover. And then we get to the tech demo instruments, which are the helicopter and MOXIE. And so they all fit into these categories, and they're going to work well together. That's the whole point of this of these slides. First of all, just to give a shout out for the helicopter, it's a cool thing. This little thing was proposed. It was rejected in the proposal phase, but NASA and JPL got together and they said, we love this as a tech demo, even if it's not scientifically valid or justified, and for this particular mission. And so JPL got the nod to go ahead with this. It is solar powered. You see the little solar panel on the top. It's got 2 counter-rotating blades, and those are 1.2 meters in diameter, so large, especially for a 1.8 kilogram instrument or spacecraft, you could say. The blade speeds go up to 2,400 revolutions per minute. That's almost Mach 1 on Mars. And so that's about the limit of what you could expect it to do. So they had to, this design really fits in a very, very tight envelope, has to fly in this Mars thin air. And it's just planned as a tech demo for about 5 flights. Flight durations up to 3 minutes and distances to 300 meters. The real kicker on this, the difficult thing, is to actually get this, is not necessarily to get it to fly. The real difficulty is to warm this thing up after a cold Mars night and get the battery to a place where it can give the rapid output of current that it needs to actually fly this thing. And so that is the really tricky balance. And so that's, we'll see how it goes. It's going to be something to watch. Now, in a sense, this is not giving us really any science on this mission, but it holds potential huge promise for the future. And that's why I'm very interested in this. So first of all, there it is. It's actually gets stowed on the belly of the rover. So this is the underside of the rover that you're looking at upside down. And it's going to have to drop off of the rover like a baby giraffe being born once it unfolds itself. But I love this concept because ultralight Mars rotorcraft could open up new ways to explore Mars, especially for those areas that are difficult to get to. And so in my view, going into a Mars cave with a helicopter is something that we've got to do in the future. And so this is an Amazonian age cave in the Tharsis region. It's got an opening 150 meters in diameter, seen from orbit very easily. It's at least 175 meters deep and probably kilometers long, lava tube. And I think that if we could go into these caves with a helicopter, do reconnaissance and come back out and radio it, it would be the first great underground exploration of Mars in a big way. And so we've been actually developing an instrument that could possibly go on this kind of this mission and do rapid surveys for organic materials in here using laser sensing. And so this just won an R&D 100 award just recently. So it's pretty cool. I'm very privileged to have a team that was working on this here. And we hope it can now go on to actually do some exploration. So back to Perseverance though. After the helicopter, we have the MOXIE instrument, which is the oxygen production unit. And this is, again, another really cool thing. It's not easy to make oxygen on a cold, rarefied atmosphere planet. And so this is basically a catalytic converter bed that will take the CO2 from the Mars atmosphere and convert it into oxygen and carbon monoxide using 300 watts, which is a lot of instantaneous power from the rover. It is only making oxygen at a rate of about 1/4 of the needs of one human being. So it's not real easy to do, but it's a tech demo. If we get serious in the future about humans, there's going to have to be some of these that are sent well in advance. We store up a bunch of oxygen and then use it for both the oxidizer for the rocket and for the humans that are there. So I love the concept. It's great that we're proving out these kinds of things. Now, in terms of the real science, there is the environmental dynamics analyzer that comes from Spain. So this is the second in a line of Spanish sensor packages for the Mars environment. And so this will have sensors on the rover deck as well as on the rover's mast. And so it's going for wind, speed and direction. It's going for humidity, thermal infrared, ultraviolet, dust, and radiation. So again, it's going to continue a lot of the environmental monitoring that we've been doing for years on Mars. And then we have another European contribution in RIMFAX. RIMFAX is the first radar to go and operate on the surface of Mars. This is provided by the Norwegian Defense Ministry. And so I suppose they're used to using it in glaciers and other places, but it should work quite well on Mars to show what strata or what changes in layering there is under the surface, mostly operated as the rover drives, so that they get these plots. And so it should go down beyond 60 meters, has a resolution of about 20 centimeters. And so I think it's going to be pretty interesting to see what we find. Of course, they're going to want to go various places where the ride might be pretty rough, but it could be pretty interesting as we get to the rim of Jezero crater and into some of the rim material to understand the mega blocks and mega breccias and so on that are happening on the rim of a crater. Maybe there's a lot of good material in the delta as well. So think about that for a sec. And then Pixel, here we come to the instruments that are on the arm of the rover. And so Pixel is an X-ray fluorescence instrument. This is the first one that really uses a micro beam. And so it has about 120 microns of resolution. And I'm sorry, I don't have a scale on the elemental maps on the right, but these are really within a centimeter. And it's made to make rasters over very, very small areas. Remember that this is a fine scale sensing rover. So it's going to be well paired with the other instruments to really do fine scale measurements. By the way, there is a rock abrasion tool on this rover, so they will be able to actually make a flat, smooth spot that's slightly below the surface, the weathered surface of the rocks. And so Pixel could work on that as well as on the unabraded surface of the rocks. Next is Sherlock and Watson. So the Sherlock instrument was proposed, and it does actually come with a context imager that is used to focus the Sherlock spectrometer. But that context imager has a fixed focus on it, and the rover engineers really wanted to have another instrument, another imager that could image the rover itself from the arm. And so they lobbied, and it's generally a good idea so that you can see what's happening in terms of wear and tear to the rover and other details. So they actually proposed to add a imager from the arm that can focus at long distance as well as short close up. And so that's Watson. It's on the right-hand side here. And that's just a copy of Molly that is on the Curiosity rover, but it's going to give us the close-up hand lens scale imaging that we want and need down to a couple of tens of microns in resolution. Very important for understanding the nature of the sediments, whether they're fine-grained material that was in suspension in a lake, or whether they were in a fluvial environment. So that's what's very important. So the Sherlock instrument itself is a UV, Raman, and fluorescence spectrometer. And it's a great idea because it's focusing on organic materials that for which Raman and fluorescence are both sensitive. And by going into the pretty far UV at 248 nanometers with the laser, it is able to separate out the fluorescence from the Raman spectra. And that's generally a big problem for Raman spectroscopy if you are familiar with it, because they tend to be on top of each other for green laser Raman and other devices. And I'll tell you about SuperCam in a minute. But so anyway, this is a great idea. It gets both the fluorescence, which is very sensitive for organics, and in the Raman, which is less sensitive but much more diagnostic. And we love the combination of those two. So here's a few words about what its capabilities are. It can get down to about 10 parts per million of bulk detection over a fairly large area, or do lower sensitive measurements in a very fine scale sense, so 1,000 ppm at over 100 microns. Now, if we keep in mind that what the SAM instrument has measured for organics on Mars, it's not these abundances so far, but SAM is measuring in bulk. And SAM also has the possibility that it's actually destroyed some of the organics that it's trying to measure as it is heating these samples up. Hence, there's been more of a focus on derivatization experiments recently. So, you know, the jury's out in terms of what we will see with these instruments. I think it's always the case that's the case when we go to a different planet with instruments. Even if they work great on Earth, they may not actually show us things that we're looking for on another planet. So that's my take on these things. And so we'll see how Sherlock does. Here's a little bit more eye candy in terms of for the Raman spectroscopists. So I think these are some demos that were done early on. The mineral signatures are on the left. One of the details of Sherlock is that with its focus on organics, it's not actually sensitive to the fingerprint region of the mineralogy. And so it starts at about 800 wave numbers with the Raman shift. And you can see that down on the x-axis of these plots. And but I'll show you, it is sensitive a little bit beyond that. So, but anyway, at the longer wavelengths, it's very sensitive, and you can see all of the many of the organic signatures here on the right as well. And that's what they're really focusing on. Here is actually a plot and some maps of a stromatolite from the Strelley Pool in the outback in the Pilbara region of Australia, and a great place, by the way. And so you can see the visible image on the left, and you can see these are domal stromatolites, which are basically interleaved carbonaceous matter with chert and so on. And of course, being 3.5 billion years old, these are the oldest fossils on the Earth. And a lot of things have happened to this. There's no longer organic signatures per se in their original form, but there is organics in the form of kerogen and so on. And so the map that a model that's like Sherlock made is on the right. You can see by the color coding that there is some organic in there. You can see it in green, and it's blended in with the blue of the dolomite, which also came from the organics because of the carbon that is now in the dolomite form, and then the chert, which is surrounding it. And the chert was, of course, the original host that entombed and taphonomically preserved these organics. And so we're actually looking at a time frame on Mars of about the same time, about 3.5 billion years ago. So This is in many senses appropriate. Also for the type of microbes and fossils that one might expect to find on Mars that would have been or might have been in existence at that time. So it's a great test. And so it looks like if we were to come across something like this on Mars, Sherlock would do the job. On Perseverance, there's now a total of 23, actually I'm told 24 cameras if you include, or 25 cameras if you include the helicopter. And some of these cameras are on the descent stage and the landing cameras. You can see there's 7 of them listed on the lower right. But then there's just a lot of cameras in both for engineering and for science and for helping the instruments to do their jobs. And but of course the queen of these cameras is Mastcam Z. It's the zoom lens stereo color imager by Malin Space Science Systems. Malin had set out to do this on MSL and it didn't quite work. He had actually tried to do 120, I believe, millimeter zoom, and it was a step too far and they had to scale back on MSL. So on this rover, they're succeeding. It's slightly more modest in the zoom capability, but actually, Horton, I hate to say it, but the long distance RMI images on SuperCam are going to not be any higher resolution, I do not think, than the 110 millimeter setting for this camera. On the right-hand side, you'll see the filter wheel allows these discrete wavelengths. And so it provides a very multispectral, very good multispectral imaging for a variety of diagnostic things, especially the oxidation of iron and potentially some sulfates and a little bit of water, potentially finding some water absorptions in the around 1,000 nanometers. So
and meteorites, right?
I'm sorry?
This is how we find meteorites as well.
Yes, that's exactly right. Yeah, and so there are 3 mechanisms in Mastcam Z. There's a filter wheel, there's a zoom assembly, and the focus assembly. So all 3 seem to be working well, and so let's hope it stays that way throughout the mission. And then I'm going to talk about SuperCam, and this is our baby here at Los Alamos. This is the proposal cover. And we wanted to show that this is an instrument that has multiple capabilities. So it's an evolution or an evolved instrument from the LIBS capability of ChemCam, and we wanted to reflect that in the name, although some people think this name is not very creative. But then we added 2 molecular or mineralogy techniques. And so one is the visible and infrared spectra, and the other is the Raman. And also we get time resolved fluorescence. And then we have color imaging, and then we added a microphone later. So actually the Viz IR was actually in some sense tough to add because everybody in the US was already working on an infrared spectrometer proposal for this mission. And but we thought we should add it. The Raman spectroscopy, while it gets good spectra, it's a newbie to space exploration, and both, as I'll show you in just a minute, both Raman and Viz IR have their strong points and their weak points with respect to different minerals, and so it's great to have both. But we had to search far and wide for a group that was not already competing against us, and so we found one on the outskirts of Paris. So first of all, just to, in case you're not aware of it, this is a short video. I hope it shows on Zoom, but just first of all, showing that these instruments are point, focus, and shoot, so they're simple in that sense. This is actually a ChemCam video, so that's the ChemCam body unit that sits inside the body of the rover. Its light comes via a 6-meter long fiber that comes down from the mast of the rover and comes into these spectrometers. And this is the mast unit of ChemCam. The laser is over on the left, and this is the telescope. The telescope aperture on ChemCam is just a couple of millimeters larger in diameter than that of SuperCam, due to having to accommodate all kinds of things on SuperCam. Here we're going to be firing the YAG-like laser. It's in the infrared, so you don't see the laser beam, but you will see the flashes on the target as it creates plasmas as it's ablating material from this nice iron pyrite target about 6.5 feet away. So there's a still image of it, and it's the analysis area is very small actually. It's only about 300 to 500 microns in diameter. So over the course of time, over 8 years, we have done these 800,000 laser shots, and it's still going. And as far as we can tell, it's still as good, almost as good as new, at least as far as we can tell, like I said. So we're really looking forward to several more years on Mars with ChemCam. And this is the spectrum that we get from LIBS. We pretty much mimic that with SuperCam as well. So we get we get all of these atomic emission spectra, emission lines, and by calibrating them, we get the elemental composition. So what we did with SuperCam was we kept the two shorter wavelength spectrometers, the ultraviolet and the violet, and then we replaced this one with a high transmission spectrometer that is more appropriate for Raman spectroscopy. The light still has to come down this long fiber and go through an optical demultiplexer that passes the light to all three spectrometers, but from there it goes through a very high transmission optical system that I could show you later. And so that is something that is new and quite a leap in technology for this mission. So this is a picture of the two parts, the two main parts of the instrument. So the body unit is on the left, and this is the transmission spectrometer right here. And then these are the reflection spectrometers behind that. One of the optical fiber bundles goes right over to here. It's hard to see. And then this is the mast unit, and it looks very much the same. It has a periscope with one mirror right here and another mirror right in the center of this window. And that periscope is what transmits the green laser Raman laser light. And so it does not go through the main telescope. Instead, it is not focused to a spot on the target. Instead, it is collimated at about 8 millimeters diameter. So we have a quite a bit larger spot for Raman analyses than we do for LIBS. And some people ask, why do these things look gold all the time? They are actually coated with a very thin layer of gold, but that's partly because we are trying to keep them thermally warm or cool, isolated from their environment. The mast unit especially has to be heated to stay at -40 or warmer, and so we use electricity from the rover to do that. And the main loss of energy is actually, it's got very spindly legs of fiberglass, and so the main loss is actually radiation to the outside walls. And if we can minimize that radiation, we do that. And that radiation is in the form of course of just photons in the infrared. And gold is a very low emissivity material. And so that's why we do that. So we have SuperCam. It has these two laser techniques. It has infrared and it has sound. You saw the flash of plasma on the left. The green laser Raman looks a little bit like this. We're actually shooting into a Mars target there from the left-hand side. Anyway, the Raman spectra that we get with SuperCam look like this. So this is done at several meters distance. Raman is a very dim technique. It's only 1 in a million photons coming back are in the Raman region. With most of the light coming back as a laser light, which we have to block. The laser light would be at 0 on the Raman shift scale here. And so it's shown in wave numbers. But you can see all of these different peaks. These are more spectrally bright targets. The spectrally weak targets we actually do not see. So you can, in your laboratory, go and get a Raman spectra of magnetite, which is a dark mineral. But this is mostly the light or bright colored minerals that we actually get. But anyway, that is what we get with this Raman spectrometer. Just a note that we actually temporarily separate the mineral luminescence from the Raman signal. So Sherlock does it by having it way in the UV where the luminescence doesn't come up until a longer wavelength. Here in the green region, we would have the mineral luminescence at the same wavelengths as the Raman signal, but they are temporarily resolved. We fire the laser, it's a 4 nanosecond laser pulse. The light travels to the target and back, and then we get the Raman signal. Our intensifier that allows us to do this sensitive work, it has a very sharp time gate, and we can do 100 nanosecond exposures. And that's what we'll be doing for the Raman. And so the end of the Raman exposure happens before we get much mineral luminescence light in there at all, with much of this mineral luminescence lasting orders of magnitude longer into the microseconds and milliseconds easily. And so that's how we make this separation. But we can also use that to an advantage to actually probe the mineral luminescence. And I think I show that next. Yeah. So these are some plots from Anne Olila, actually. And here she has plotted out luminescence from a Durango apatite that she was probing with SuperCam. And on the left-hand side, you can see there are some Raman peaks. They're labeled R or Raman. But next to them, we're getting these big peaks from luminescence in samarium, europium, dysprosium, and neodymium. And but these are all coming later. So this is with a long delay, or sorry, not a long delay, but with a long exposure time. And I actually don't have the exposure time, but the delay here you can see as you go to longer delays, you don't have the Raman anymore, but you have these in different time scales. And the neodymium actually decays quite rapidly here, but the other one's not. And so that here we show another, or I guess, yeah, it's another peak of neodymium. And then on the far side here, we're showing the decay curves of these different species. So we're going to have some fun with that. It's a little bit of a side project in a sense. But the cool thing is that the organic fluorescence actually occurs simultaneously with the Raman. And so even if we're time gating this at 100 nanoseconds to just get the Raman, if there's enough organic materials of the right kind on Mars, we're going to see them in a bunch of fluorescence at that same time. So we'll be using that as an organic probe as well. Unfortunately, we really didn't do much work on that at all in the development period of the instrument. A lot of times there's things that we think we're going to get to and just never do, because the hardware has such a priority and it's challenging. We run into all kinds of problems, of course. So that was maybe a bit of a faux pas that we did not actually do that kind of research. But we're getting a lab unit, and by early next year, we should be able to do some of this kind of work. Now, the other part of the mineralogy is the infrared, visible and infrared spectra. And so this is what we get for the infrared range. It's from 1.3 to 2.6 microns. It's 256 channels. It uses unconventional spectrometer technique. It is not a grating. It actually uses an acousto-optic tunable filter to scan across the wavelengths. And so we have each scan will take up to 80 seconds per observation point on Mars. And we get these 256 channels, and you can see the output of each channel and in a smoothed line. And then here's a laboratory calcite as well, just for comparison. So it's going to be diagnostic and really great. The only time we could really make measurements with this was when the whole rover was in a thermal chamber, because the instrument has to be cold, otherwise we get excessive noise in the infrared. And then just to point out that I think I had in this previous slide up here, I had these little bouncing molecules on the side, just showing that that Raman and infrared tend to be very complementary in the minerals that they can actually detect. So Raman, when Raman is detecting symmetric stretches, the infrared is inactive. And then when the asymmetric stretch is measured, it's IR active, as well as the bending mode, but Raman is inactive. And so these are very useful to have with each other on the same mission. And so we're excited about that. You know that on the Mars orbiting instruments, Prism and Omega, these spectrometers, they are infrared spectrometers, and they've been really great at detecting mafic minerals, but not so good at detecting the felsic minerals. And so we were quite surprised when we got in Gale Crater and found so much feldspar that looked like it was from the rim. So we think we've missed some of the story, even of global Mars, by focusing too much on a technique that is somewhat limited. And so we just always have to use the different techniques complementarily so that we can get the whole picture. And so that's part of our rationale for putting these both on this one instrument. And we're, like I said, we're excited about that. Now, both ChemCam and SuperCam work in raster mode. So we have we do observation points, and the laser creates pits, and so we'll do that. We can even shoot down the drill hole, which is going to be really good for documenting the types of samples that we are caching to bring back to Earth. Now, SuperCam has different spectral footprints for these different techniques. So first of all, taking the same rock, which is Nina Lanza's favorite, it's Stephen, it had this manganese in it. First of all, you can, and it's about the size of a penny, by the way, the whole rock is, but you can see that the dust is way off on the side here, not where we shot, and that's because the LIBS plasmas have a shock wave that removes the dust. And so that's going to be useful for all the techniques. We do the LIBS first, and then we can do the other techniques. Now the LIBS spot size is 300 to 500 microns. It's smaller than the other techniques. Raman and the VIS passive spectroscopy have 3/4 of a milliradian. So at 2 meters distance, that's 1.5 millimeters. So that diameter is 3 to 5 times what the LIBS is. And so even if some people are worried that we're going to damage the mineral by the LIBS, but it turns out that we're only hitting a small fraction of the Raman footprint with the LIBS. But we still remove all the dust pretty far away. Okay, then the infrared is actually a little bit larger field of view, but they're all still co-Bohr sighted. So we'll have to be a little careful with interpretations because they don't probe exactly the same field of view. Then there's a microphone, and this was an addition that actually our French colleagues were most interested in. We were kind of said, well, aren't we doing enough? But they wanted to add a microphone, and I'm really glad that they have. Now Nina here at LANL is working on acoustic signals as well for SuperCam. What a student, Baptiste Chide, has shown, he's a student in Toulouse, France, is that if we take the laser pulses from the LIBS and we plot them, this is the number of laser shots up to 150 in one burst of laser shots on the same spot, the sound actually changes over that burst, and it changes more for soft rocks than for hard rocks. And if down here you have a plot with the Victor's hardness on the x-axis and the decrease in sound intensity on the y-axis, and it more or less makes a log linear plot there. So we believe we will be able to use this for a number of things, but one of the most diagnostic is the hardness of the rock that we're actually shooting. It can also be used for environmental studies, wind turbulence and temperature and things like that. So we're going to have a lot of fun with that microphone, no doubt about it. Okay, here's a few fun photos. So this is actually installing the mast unit on the rover. Up on there, people are standing up on some scaffolding right above the rover actually, and this is the whole mast of the rover with the NavCam imagers there, the elevation gimbal right there, and so SuperCam gets the sort of the prime spot right at the top of the rover. And here are some of our folks at JPL testing. So you can see the rover on the right, the mast unit is right there, the mast of the rover. And then they're shooting at a target that's up on this stand right here. And you can see they're taking a picture and everything. And so this was right during the Mars 9 conference last year and a third ago in summer. So here they're taking a picture, looking at the picture, and I'll show you that picture if this video works on Zoom. So Oh, and I'm afraid the sound isn't going to come across, but they're oohing and eyeing over the first laser shots from the rover here. So that was a cool moment for us. Here we were in the control room right next door, taking a look at the data as it came down. So some fun on Earth with the rover. Now, looking at the landing site, some of you may have been involved in the landing site competition that went on for several years, but Jezero Crater won out. It is 17 degrees north latitude, and it's another crater lake, but much smaller than Gale Crater with Curiosity. And so here it is. It's about 45 kilometers in diameter. It has both an inlet valley and an outlet channel. And so we know that it was a crater lake. It's right on the edge of the Isidis Basin and near some other areas that people have been interested in the Syrtis region. So the circle shows what we expect is the landing ellipse. That landing ellipse actually overlaps part of this deltaic feature, which is really cool. The rover's landing has one more feature added. It's still going to be the sky crane like Curiosity, scary as that is, and I hope you say your prayers for this landing. But that one new feature is something called TRN, or Terrain Relative Navigation. Basically, as this is coming down in the parachute, the sky crane and the rover then separate from the back shell and the parachute, and they have to actually divert in one direction or the other to actually avoid the parachute, which is still descending. And that divert maneuver, instead of being in a random direction, is now going to be in a targeted direction to try to avoid whatever might be hazardous terrain below. And so it has one choice as to where it's going to head, and it just goes in that one direction. But it could land on the delta. It's going to try to avoid the edge of the delta, the cliffs and things like that. This is always a probabilistic thing, so there is always some small percentage chance that it's not going to make it due to hazardous terrain. And you and I as geologists know that the most hazardous terrain is usually the most interesting place to land. So there's always a trade-off in that. So we'll see what happens. But Jezero Crater is extremely fascinating. We have what we think are mafic materials, possible igneous material on the surface of the crater. Then we have all of these clay materials that are easily seen from orbit in the delta formation itself. And then as a bathtub ring around this crater, we have these carbonates. And as you probably or perhaps know, carbonates are very scarce on Mars. And in spite of the fact that Mars has a carbonate atmosphere, carbon dioxide atmosphere. And so we're trying to understand, by going to these carbonates, what makes this carbonate ring around the edge of the crater there, and why is it there, and what can it tell us about the lack of carbonates in the rest of Mars? So some very interesting global questions that we can raise on this mission. So here's sort of a tentative notional idea of a traverse. If we land near the delta or on the delta, then we'd be right there. If we land farther away, we can actually study some delta remnants and then go to the delta, eventually study the lake margin that is carbonate rich, and then go on to the crater rim. And for the first time with a rover, really study a large crater rim of this size, and then perhaps go beyond. But of course, the sample caching is part of what we're going to be doing. And so that's going to play a role in where the rover goes very clearly. So the sampling is being done with the drill core. I hope you can see this short video. There's no sound with it, but it shows the coring drill going in and then taking the cores to the sample cache system, or SCS. This is a big region of the front of the rover. First, the core is in a metal tube, and it goes down with a turret down into the sample cache system. Another arm actually retrieves it there, and then that arm takes it past an imaging station and a capping station, and then on to storage. We're not going to show those different stations here. It's just going straight to storage to make us a nice fast video. But we certainly hope all these mechanisms work together and work well. so that we can cache these samples and then eventually deposit them on the surface of Mars. And I know that there's at least some people at UNM who are on a MEPAG committee that's hopefully going to help with some of the advising of this. So here's an image of the type of cores. They're about 1 centimeter diameter and a number of centimeters long. And there is a capability to get a regolith sample as well. So that's kind of cool. And this is a picture of those sample tubes going into the rover. This was taken in late May of 2020. And I can tell you personally that there were many weeks where I was very concerned this rover would not launch this year. So when this came from JPL, it was the very last thing that went on the rover, basically. And by the way, the SuperCam calibration targets were the second to the last, I think. And then this rover got packed up. And in fact, here, there's a really cool picture because you can see the wheel. One of the wheels is here, and it is all it's all wrapped up already with sterile material, so that it doesn't because anything that touches the surface of Mars needs to be sterilized. I think here's some of the retro rockets. This is actually the cover of the helicopter right there, so that's got to get jettisoned. This is all part of the belly of the rover. So really cool picture. And so the sampling, this is something that we're going to have a lot of fun watching. I hope those of us on the payload system don't get too much headaches from, but the samples are going to have to get deposited somewhere. We want them deposited before the rover has any troubles. And so we're probably going to deposit some early and then maybe go out to more risky areas, come back with more samples, put them back in the same sample depot. We may actually create several sample depots with these 38 tubes because you could imagine you might want to put one down early so that you have contingency, but then go on and actually go to a more interesting site. And then it'll drop these on the surface. And so you could imagine that we actually maybe will take replicates of some of these with the idea of more than one sample depot. And so we'll see how that all goes. It's a very interesting concept and going to be fascinating what we end up doing. So this is only the first of what needs to be 3 missions to make this a sample return set of missions. And so NASA is already putting money into the next mission, which is the Mars Ascent Vehicle. It will also have a fetch rover because they're not completely sure that Perseverance would be alive at that time. We certainly hope it is. I like to see these rovers as 15-year missions. But anyway, that gives them flexibility with the mission. And then the third mission has to be because this small rocket, which will just take the samples off the surface of Mars, only goes to low Mars orbit. And so then you need a rendezvous and a larger craft to get them back to Earth. If you watch the movie The Martian, it's kind of like that. And so that's how it's got to happen. So we had a successful launch on, I'm sorry, not July 20, but July 30. And the landing is scheduled for February 18. So just make a mental note, that's 4 days after Valentine's Day. So we all hope to be watching and have a successful landing at that time. So with that, I'm just going to conclude by saying this is a really exciting mission. It comes on the heels of Curiosity being still being extremely exciting, but it's just a great privilege to be a part of both of them. So thank you very much for your attention.
Wow, terrific. Thank you, Roger. It's very exciting to see the full overview at this stage. So do we have anybody who wants to ask a question?
Yeah, I have a quick question. I'm interested in the sampling tubes. Like, what are they made of and how thick are they?
Yeah, they're titanium. They are, I believe, coated with an anodizing material on the outside to give them a cooler temperature on Mars. Because bare metal would warm up to a pretty high temperature in the sun on Mars. And I do not know their thickness, but they are relatively thin, of course, to be lightweight and to
Mhm.
conserve space within the drill
Well,
core.
I think I read somewhere about 1/2 a millimeter. Does that sound right?
That sounds reasonable, yeah.
Okay. Thank you.
And I know that they were very careful with the alloy of titanium just to make sure that they didn't have, too many elements in there, too many things that could actually act as possible impurities when we do the analyses later.
Mhm. Okay, thanks.
Okay, any other questions right now? I'll mention one thing, there's obviously the sample group, but presumably when the samples come back, they will also be made available. I know we have a group with Adrian Brearley here who's expecting samples back from 2 asteroids in the near future.
Yeah.
So I'm
Yeah,
assuming
that's
that.
really exciting. Yeah, let me just say maybe a little bit more about the organization. I think it was almost 2 years ago, there was a group that was, well, actually, let me go farther back than that. There was a group that was sort of self-appointed who were helping to advise on the development of the sample cache system during the development of the mission. That group was disbanded, so a couple of years ago, and then there was a competition for return sample scientists. And so that group was selected. It is now meeting together, and they are going to be and are participating in the mission now, including a number of people. Now the ESA also was given the opportunity to add several scientists, and so we have about 4 new scientists from ESA as well. And as you may be aware, ESA is being courted to help with the sample return missions. So that's part of what they are getting for that. Then there is supposed to be a instrument focused participating scientist group as well. They have not actually been selected, although the proposals went in over half a year ago. And then finally, I think there is a MEPAG group that has also been stood up, which is, I think, providing a little bit of outside advice or ideas. So there's a lot of people involved in this in one way or another.
And a lot of those people either have a connection to UNM. Chris Hurd got his PhD at UNM. He's on the sample selection. And we heard about Nina and Ann, who also got their degrees. And we have Roberta on the online too, is helping with KimCam, and I assume she'll be doing maybe doing Perseverance operations. So that's very neat.
Yes, she just joined our team, so yeah, for Perseverance as well. Yep.
Very good.
And Amanda Sheridan as well, who's online.
I think the other thing that there's a whole incredibly interesting story you just barely touched on regarding Jezero Crater and the what we might find there. So what are you particularly looking forward to finding out about Jezero and the landing site, Roger?
Yeah, good question. Let me see if I can actually put it back up again. Yeah, I mean, oops, it seems to be stuck. We'll see if it moves eventually.
I see your slides.
Yeah. Let's see if I can actually get them moving. There we go. Now I'm backwards. See if I can go. It's not going the other way. There we go. Yeah, we'll get there. So Jezero is, yeah, it's absolutely fascinating, and it was picked for several reasons. One is, let me go one further back. One is that we want to have a datable sample, in other words, an igneous sample that will tie together crater count ages to actual radiometric ages. And that's a big goal of the mission. There was a lot of discussion in the landing site workshops as to whether this unit right here, which is mafic, is an igneous unit or not. And we really don't know, or it could be an ash layer. So we'll find out when we get there. But if it is igneous, then we could really get that those samples and do that datable correlation. That's not particularly my most interesting thing, but I have a hard time saying what is my most interesting thing. We are, because we've been exploring Gale Crater, having some quite diverse chemistry and mineralogy is an important thing for me to understand Mars as a whole planet. And so having the carbonates there is exciting for me. And I will want to see what that looks like. We think that the carbonates are a product of weathering of olivine. And so you have serpentinization, which produces serpentine, some talc byproducts, and then carbonates in the presence of carbon dioxide. So if that's the case, we would like to see the whole suite of these different things. And so on our calibration targets on the rover, we have carbonates, but we also have a serpentine, and we have some magnesium-rich materials as well. So we're really hoping to see some of that. But Horton, to answer your question honestly, I am looking forward most to the things we don't expect. And so it's what those are going to be. But that's the nature of Mars exploration so far still, and I think for probably several missions to come yet. So I hope that's a reasonable answer for you, Horton.
Yeah, thank you. Thank you very much. And we really appreciate your talk. And I know the talk's going to be posted, which we appreciate. So thank you, Roger. And our group here at UNM is working hard on a range of these Mars-related issues. So we look forward to being involved. As we go forward, we still have a lot to do with ChemCam and Mars Science Lab as well. So it just keeps getting more and more exciting.
Yeah, absolutely. And there may be others up here that will be happy to give talks in the near future as well on their more focused aspects of what they're doing.
Yes, thank you. Okay, well, have a great afternoon, everybody, and evening. And I guess we'll see you all at the next seminar.
Yeah, thanks again. Bye-bye.